Hello. In this video we will build a classification model using sklearn, and we will optimize parameters of this model via grid search and k-fold. So our dataset consists of expression levels of different proteins obtained from 38 control mice and 34 mice with Down syndrome. So we are going to predict whether the observation came from control mice or mice with a Down syndrome. Let's download the data. So you could either download the data from the URL, or once you download it, I suggest you to save it to the local CSV file so you don't download this data every time you run this cell. So I've already downloaded and save it. So I could simply load it from my local directory. Mouse protein data. So let's see how it looks like. We have 82 different columns in this table, including the genotype column and the mouse ID column. So let's set this mouse ID to be an index of our data frame. So data set index mouse ID. Now you see that mouse ID become an index of our table. Unfortunately, some of the columns contains missing values. So let's also sort this, sort values. So you see some of the columns contains like 1080 minus 795, so about 400, about 300 of missing values. So for the sake of simplicity, we will simply drop all the columns that contains at least one missing value. Data equal to data drop, and the axis 1 corresponds to columns and how equal to any. So what happens here, so instead of 85 original columns, we had 32 columns that doesn't contain any missing values. Okay, so as features we will take all the numerical features and we will drop all these categorical features. And as for our y, we will use a genotype column. So our x is equal to data.iloc. So all the rows, all the columns up until 28th column. And y is equal to data genotype. So this is our x. 28 features, different protein expression. So let's split our data into training and test parts, and our test part will be completely unseen. This part we will use to validate the performance of our model after we train it and optimize the hyperparameters. And we will use a very specific split on a train and test. So we will see in the end why this matters in this particular case. So as for classifier, we will start with a key nearest neighbors classifier. We will use a grid search CV from sklearn, and we will use k-fold. Particularly, we will use 5-fold cross-validation to estimate model performance. So as always, we start with creating a cross-validation class, k-fold, with a number of splits equal to 5. We will set parameter shuffle to true, and we will fix a random state for reproducibility purposes. This is our CV. So our classifier is a k nearest neighbors classifier, and we doesn't need to set any parameters here. But what we do need to do, we need to define a grid over which grid search will search. So the grid, let's make it params grid. We will only grid over number of neighbors, again, like for simplicity. Neighbors, let's look between 3 and 22 with a step 2. So what is it? It's all the numbers between 3 and 22 with step 2. 3, 5, 7 up to 21. So I decided to use an even number of neighbors. It's a reasonable thing to do. So our grid search will be equal to grid search CV. So the first parameter is an estimator. In our case, it's a k-neighbors classifier, CLF. Param grid is equal to params grid. And CV is equal to CV. Okay, so we fit this grid search X train, Y train, and guys, if you don't understand what is going on here, you need to watch previous video. So I fit a grid search. Let's display the estimator with the best set of parameters. In our case, we only have a single hyperparameter. So what is the best number of neighbors? gs.best estimator as the KNN classifier with a number of neighbors equal to 3. And what is the corresponding model performance computed on a validation set? So quick reminder, the cross-validation, the k-fold cross-validation means that we split our data into k parts, and we train k different classifiers with a fixed number of neighbors. In this particular case, it's 3. We train them on a k-1 parts of the data. We predict them on the kth part of the data, and we average the results over k validation folds. So the corresponding model performance is so gs dot best score, and it's very, very good. So this is an accuracy score, and since our classification tasks is more or less balanced, so if we, let's say, y train value counts, so it's about the same number of control mice and number of mice with Down syndrome is about the same. So the accuracy is a good metric to use here. So let's compute the, so this is the accuracy score, but let's compute a prediction on the validation folds. So for this, we will again use a cross-val predict. So the reason why we want to compute a cross-val predict, because instead of accuracy score, we might want to compute some other performance metric for binary classification, and we will compute a confusion matrix. So basically the number of true positive, false positive, true negative, false negative. And for this, we do need actual predictions and not the performance score. So ypred is equal to cross-vals predict, and the estimator is gs best estimator, or we should use k-nearest neighbors with a number of neighbors equal to 3. And this is like, okay, x, y, and cv. So this x train, y train, cv equal to cv. So this is our predictions. This is so-called out-of-fault predictions, which means that this prediction, for example, this prediction for the very first observation was computed by the model, which was trained with a set of faults which doesn't include this particular observation. Okay. So what is the accuracy of this model? Let's just quickly check it. It should be the same number, accuracy score, between ytrain and ypred. So pred stands for predicted. Yeah, it's completely the same, so it's fine. We're all good. Now let's compute a confusion matrix between ytrain and ypredicted. So again, the confusion matrix is also is pretty good. Most of the observations are either a true positive or the true negative. And a quick reminder, what is that? So if you solve a binary classification task, there is this very important matrix called confusion matrix, and this matrix basically shows how many errors of different types your model made. So if you predict that the observation is of class -1 or -1, and your model predicts this observation as a 1, then this observation is called true positive. So it has positive class and it was predicted as a positive class. So if your observation is of negative class and it was predicted as a negative class, then this observation is a true negative. If you made an error, then there are two types of errors, and depending on the task that you solve, one error or another may be of more importance. So the type 1 error is an error when you predict the observation as a positive class, but it is actually a negative class. And vice versa, type 2 error is you predict an observation as an observation from a negative class, but it is actually a positive, it's observation from a positive class. And obviously these things are like interchange as you swap the positive and negative class, but it actually depends on a domain task. For example, if your goal is to predict pregnancy, then it is reasonable to say that the positive outcome is like the woman is pregnant, and negative outcome is woman is not pregnant. So whether you call class a positive or negative class is mostly defined by a domain and by a task. So this is very important matrix because there are actually dozens of different performance metrics based on this confusion matrix, based on different combination and normalization of these 4 numbers. And during the lecture, you will be told about different types of metrics for binary classification. Okay. So basically, what is going on here, we have this vector ytrain. It's a vector of true labels, and we have this vector of ypred, which is a vector of predicted values. And let's list them for y1, y2 in zip, ytrain, ypred, print y1, y2. So every time when our observation, so first is a true label, second is predicted label, every time these two labels coincide, it's a true positive. Every time it's coincided, it's control, it's true positive. Every time it coincides coincide, and it's TS like 65 DN. It's a true negative, and every time it differs depending on how it differs. So whether the first is controlled, whether it's truly controlled but predicted as a has Down syndrome, or vice versa. It's either a false positive type 1 error, or it's false negative type 2 error. Okay, so this is just a quick reminder of what is type 1 and type 2 errors. So now we train a classifier. We grid search for optimal parameters of this classifier. So we end up with a k nearest neighbors classifier with with number of neighbors equal to 3. So what we are now interested in, we want to evaluate the performance of this classifier using completely unseen data, right? So we already have a classifier stored here, best estimator. So let me show you the type of this thing. This is you see, it's a k neighbors classifier. So we could invoke method predict, and we want to predict our unseen data. Let's store it in the variable y test predicted. And now we could compute an accuracy of our prediction, right? And it should be pretty good. So y test versus y test predicted. Whoa! So this doesn't look right. So it's actually this accuracy drops like significantly. It was like almost a 100% accuracy, but it becomes basically a random guessing, like 50-50, and we have a balanced target in this binary classification. So what is wrong here? So let's also compute a confusion matrix to ensure that y test predicted. And we could see that like this type 1 and type 2 errors are very large. So what happens here, we actually overfit our model, and the reason we overfit our model is very simple. So this particular data contains about 1,000 of rows, right? But the problem is that it contains multiple observations from the same mice. Okay, so it only contains 38 mice, and from every mice we have 15 measurements. And the problem is typically when you have measurements from a same person, from a same animal, these measurements will be much more simple, much more closer to each other than the observations from different people, different animals, but of the same class. And therefore, instead of actually solving a classification task, your model will overfit and will solve a class of determining the person or the mice, a mouse ID in this case. Okay, so let me illustrate what am I talking about. So this is a scatter plot. So I've took some subset of data, and I took observations from 3 mice, and all of them, like 45 observation in total, 15 from each mice. And we could clearly see here, for example, so this is a pairwise scatter plots for 4 different features. We could clearly see that these observations probably come from the same mice, and these observations from a second mice, and this observation from a third mouse, right? But what if I told you that, and this is completely true, but what if I told you What if I told you that two of them are healthy mouse and one of them is a mouse with a Down syndrome? We, like, watching on this scatter plot, we could clearly see that the observations from the same mouse are pretty similar, you see? But the difference between observations of the two mouses of the same target, so two healthy mouses, right? This difference is almost the same as the difference between two mouses which are like healthy and with a Down syndrome, you see? And for some features this is the case, and for some other features we just cannot differentiate these points based on these features. So the similarity or the difference between the observations from two different mouses is bigger, the difference is bigger or like the same as the difference between two mouses of the different class, okay? And the similarity of two observations from the same mouse is pretty high. So what happens when we make a cross-validation part? So actually my train test split, the original train test split, this one, right here. The reason I do this specific non-train test split from an sklearn is that I put the like my test observations only contain observations from the mice that are not in the training set, okay? And when we do a cross validation, so this part, k-fold, we do not use information about groups. So we end up with some training folds. We end up with some mice which observations are also in both in a training part of the folds, training folds, and a validation folds. And this is not good, because and this eventually it leads to the overfitting. Okay, so what then should we do? So instead of a usual k-fold, we should have used so-called group k-fold. So group k-fold ensures that all observations from the same mouse will either be in a train fold or it will be in a validation fold, okay? So if you have multiple observations from the same mouse, they either all be in the training part or it will be in the validation part. Okay, so how we do it? So let's import this group k-fold from sklearn. Group k-fold, and like the code is pretty much the same. We just change usual k-fold with group k-fold. So we change that to group k-fold, and also there is some difference in the implementation. So cv is equal to cv.split. We have to manually invoke split because the information about the groups is taken by a split method. And previously we need to define the groups obviously. So the groups is equal to x trains. Yeah, x train. Let me show you. So you see the mouse ID. Mouse ID consists of two blocks of numbers. First four letters is a mouse ID and second letter is observation ID. So what we need to create a vector that contains information about mouse ID and only mouse. How we do that? So our groups is equal to x train index map. This is the one possible way to do that. Map lambda x split. So this function will be applied row wise. So it will be applied to this thing. Split divided the string by a symbol you provide as an input to the split, and we need to get a first element of this list. So we need list thing. Let's watch on these groups. It looks right to me. Okay, so we had our groups, X train, Y train, and groups. And the remaining part of the code is pretty much the same. So grid search, param grid, X train, yeah, all the same. So the only thing is changed is our CV. We run the cell. So what is the best validation score now? GS best score. It significantly drops, right? And the reason it drops, so it was like around 97 accuracy and it's about 60 accuracy. And the reason is this 97 number, it was just an overfit, okay? And what is the best number of neighbors? And I remind you that the original best number of neighbors was 3. And for KNN, 3 is typically meant that you overfit your model because it's too local information, right? Not very general. So GS best model, best estimator. We could see that the optimal number of neighbors is 11. And what is our performance of our model on the unseen test data? So y predicted test is equal to gs dot predict x test, print accuracy score, y test, y predicted test. Okay, so the accuracy of this estimator is about like random guessing. So one thing that we forgot to do, and yeah, of course it was intentionally, is we forgot to normalize our data. And the k nearest neighbor is, if you use a k nearest neighbor model, k nearest neighbor classifier, then you must normalize your data, because otherwise, if you have some feature which changes in a huge range of values, like let's say you have a feature that changed from 100 to 1000, and then you have multiple features that changed from 0 to 1, then this single feature which changed from 100 to 1000, it will overshadow all other features, because in KNN you computed distances between 2 points, and the Euclidean distance is a sum of coordinate distances, right? So before you run a KNN, you must normalize your data, and we actually know how to do that. We will just use a min-max scaler. And on the last lecture, Mikhail show you a method to create a pipeline. So we will create a pipeline. And on the last seminar, we do it manually. So we manually normalize a training part of the data and then apply this transformation to a test part of the data. But we could do it using a sklearn pipeline. So pipeline, I forgot to run the cell. Pipeline. And pipeline is basically a list of steps, sequence of steps. So the first step is applying a min-max scaler, and the second step is applying a k nearest neighbors classifier. We also need to define a cross-validation. So the cross-validation is pretty much the same. So all the things is pretty much the same. Instead, the only things that differs is instead of simply k nearest neighbors classifier, now we use a pipeline, pipe which uses k-nearest classifier as a second step, and the first step is scaling the data. And this pipeline allows us to remove like redundant step when we compute the max min values of a train part of the data and then apply this to the test part. In this like do it automatically and correctly. Okay, so let's run this. Okay, we have a trained model. Let's see a performance of this model on an inner validation out of fault observations. So our best estimator is an estimator with a neighbors 11 and best score. So best score is again around okay, I forgot to change the CLF to the pipe. I forgot to change CLF to the pipe. We have an error. The reason we have an error that the name of our parameters is no longer an n neighbors. It becomes k-nearest neighbors classifier double underscore n neighbors. So now it should work fine. Yeah, cool. So this is our best estimator. The number of neighbors become 15. Our best score. You see the score slightly goes up. So let's make a prediction on an unseen test data. Is there any improvements there? So y pred test, and again the code is pretty much the same. All that differs is that we use a min-max scaling in our pre-processing, and like, this class will apply all the things automatically. So y test, y predicted test. Okay, so we see it's no longer a completely random guessing, right? It's not too good, but it's not a random guessing. 0.6 accuracy is not a 0.5 accuracy. Okay, what could we do next? So one thing that we could do, we could try to use a different classification approach. So instead of k-nearest neighbors, we could use a logistic regression model. Let's do it. And again, the only thing we need to change here is our classification model. So it's as easy as that, right? So we simply changed the k-nearest neighbors here by a logistic regression, and we need to change the parameters grid because logistic regression doesn't have a parameter number of neighbors. It has parameter C. The C is the strength of the regularization. So I actually forgot the name, how it call it. So it will call logistic regression and then double underscore C. And the range of reasonable parameters are typically, like it's the same as for linear regression. So it will be numpy log space, let's say -9 to 1. And let's test 30 different values of C. Let's fit a model, and let's check which parameters are the best. GS best estimator. Best estimator is a logistic regression with C equal to 0.92. So now we could assess the performance of this optimal model on the completely unseen data. GS best estimator dot predict x test, save it, y pred test, and we compute an accuracy, and okay, so it's a slight improvement, right? It was a 0.6 accuracy, it became 0.63 accuracy. Not too much, but not bad. So what could we do next? Next steps, basically there are two options, or like you could do it both. So the first thing, as you could remember, we actually dropped like 50 of the columns in our data. So our original data was, okay, so our original data was like 82 columns, including one column for target column, and we drop like more than half of the features because they contain, so we end up with 28 features because most of the other feature contains missing values. So instead of dropping them, we could try to use some imputation approach. For example, you could use a simple imputer from an sklearn. It allows you to impute missing values with a mean value or with a median value. Or you could use different approach to, so instead of imputing it with using an sklearn, you could simply impute them with some like ridiculous numbers like -1 and create an additional column that will indicate that this particular observation has a missing value in this particular column, or some other approaches to impute missing value. And second thing you could do is to try a different classifier. So we already tried the KNN and we tried the logistic regression. What you could do, you could try a decision tree classifier. And nice thing about decision tree classifier, it actually doesn't, you don't need to scale the data. It's a specific feature of a tree-based methods. Or maybe you could use an SVM or something else. Okay, so this is it for this video, and goodbye.